So this video will introduce a couple of the phenomena associated with the bending of light, that is refraction, which are Snell's law, and then a numerical quantity that shows up with it, the so-called index of refraction. So you definitely see a lot of this in your first lab, but this is a water tank with the upper half is just empty, so air, and the bottom half is water, and it's got some angles marked on the side. And what I can do is move this around, and what you see is that the light bends as it goes from air into water. So here it's at 60 degrees on this marked out angle meter, and here it's at about 42. So I'll actually remember that number. So 60 degrees from the normal in air and 42 degrees in water. And then I'll really quickly spin it to the other side to see a couple other phenomena. So one is, remember that light doesn't care which way you take. So you can reverse a light ray and it's still a pretty good light ray. So if I went to about 42 degrees here, I would be at about 60 degrees. So again, 42 in water, 60 in air, 60 in air, 42 in water. And then secondly, you see this neat phenomenon, which is when we basically break the ability to bend light going from a slow to a fast medium. So here I'm refracting, I'm bending, I'm bending, I'm bending, and then all of a sudden I'm reflecting. So that's what's called total internal reflection. So bending, reflecting. And we can see this as well in some slabs of, for instance, acrylic medium. I just happen to have some slabs of acrylic medium because, I work in a physics lab. And so you can see the bending of light very clearly. So bending going in, bending coming out. And this is the really interesting one, is if you come around from this side, take note on lab 1, I can see total internal reflection, which means that the laser light isn't able to leave the medium. And again, we can see it with this D-shaped lens. The nice thing about the D-shaped lens, again, is that if I shoot at the center of this, it always hits this side, the D side, the curved side normal. So there's total internal reflection, and then just plain old ordinary refraction. And that happens when my refracted angle gets to 90 degrees. So 70 degrees, 80 degrees, nothing, reflection. Okay. So the problems that you'll see in the textbook might be a little bit sterile, but refraction of light has a whole bunch of really important consequences. So this is the observation again, light ray comes in, this would be air, this would be water, and it bends. So that's a static picture of what I was demonstrating to you guys. There's the definition of refraction, the bending of light as it goes from one media to another. This shows up in a whole bunch of places that you see in everyday life. So first there's just the visual distortion of looking at your friend when they're standing half in a pool of water and their legs look funny, right? Or drinking straw that's halfway out of a glass, so who cares? Well, this also shows up and is the essential phenomenon behind rainbows. So there's this idea that not everything gets bent the same amount. So blue light might get bent more or less than red light, and we'll talk about that. In fact, it's also why a lot of gemstones are so pretty. So diamond is actually translucent, but you see all these rainbows coming out of the diamond because the blue light will be bent more or less than the red light. And again, we'll figure out which one is which. The twinkling and twinkling of little stars is actually kind of unwanted refraction for astronomers, because what that is the light from the star entering the Earth's atmosphere, and the Earth's atmosphere is sort of like a choppy glass of water, and it bends different parts of the light in different ways. And then finally, and from a technical standpoint and economic standpoint, really, really important, is that fiber optic communications are made possible by a refractive phenomenon, namely that total internal refraction. So really low loss, high quality communication is refraction is responsible for that. So this, you don't need any sort of technology to see somebody standing in a puddle of water. So people had been describing this for a long time. I think, even maybe 400 or 500 years before Snell, people had described this. So we'll call this medium 2 and medium 1. So medium 2, medium 1. And basically our first task is to come up with some unified way of describing these angles. So you don't have to, but we did. We chose to measure things from the normal. So this is normal to the surface. Normal to the surface means coming off of the surface at a right angle. And this is how we're going to measure our angles. So just kind of non-cartoonifying that picture, I've got a light ray coming in and a light ray coming out. And this would be what we call theta 1, and this would be theta 2. And again, the observation, without really even needing to know what n is, this so-called index of refraction. So n is defined to be this thing called the index of refraction. You can use this, and people use this for hundreds of years. So what I could do is I could just say, like, well, the index of refraction of vacuum, absolutely nothing. You know, the least medium that could possibly have light going through it is nothing itself. And I could define the index of refraction of vacuum to be equal to 1 exactly. And then I could start measuring things as it goes from vacuum to air, or vacuum to water, or vacuum to diamond. And I'll just give a couple of these numbers so you can have kind of a, you know, in the back of your mind estimate of how to think about indices of refraction on the scale of vacuum to diamond, I guess we'll go. So n air is pretty close to n vacuum. In fact, for the purposes of this class, you're not going to break any online homework problems by using 1 for air instead of 1.0003. They'll tell you if they want you to use the precise value, but air is basically 1. Water is about 1.33. So you definitely see some bending as you go from air to water. And then glass, yeah, there's no real single value for glass because there's a lot of glass. 1.4 to 1.5 is about right, so I'll just say about 1.5. And then I'll put up one exotic thing, and diamond is 2.42. And you could just find these by measuring this. So in fact, we'll actually find or show how this would work by measuring or using our numbers that we really quickly pulled off of the laser water tank demonstrator to see how you would get n water based on an experiment like this. So what we got or observed, and maybe you just believed me as I rattled off numbers, was that the angle relative to normal for a light beam coming into water from air at a value of, yikes, 60 degrees ended up in the water at a value relative to normal of 42 degrees. So 60 degrees from normal, that would be this, and then 42 degrees once it got to water. So we can use Snell's law to figure out one of these unknowns. So we know that n air is about 1, so I'll use 1. And then, so we use 60 and 42, sure. So the only trick to using Snell's law is make sure that things match. So I'll just use the subscript A for air, and then water is W. So these are measured relative to the normal, so we got 1.0003, if you wanted to be fancy. Sine 42 degrees is n water, that's what we're trying to figure out. Sine, oh sorry, we did 60 and 32. Either one actually works. 60 and 42 degrees. And then math happens. I know what sine 60 is because it's a nice number, which is why I chose it. And I would get this equals 1.33. Right? So that's how you would do this empirically, and that's how these were found originally. It turns out that something else is going on. And what this index of refraction actually means is it tells you how fast the medium actually allows light to travel through it. So I don't know, we'll call this like 1,000 years later. It turns out that n is actually defined as alternately the speed of light in vacuum, which is c, denoted C, relative to the speed of light in that particular medium. So you don't know, didn't realize we were doing this at the time, but what we were really doing when we were just sketching some numbers off of this wheel full of water, and when we found this, and it was very easy, is we actually found the speed of light in water, because we know the speed of light in vacuum. In fact, that's one of the things that in the calculus-based class you prove, is that the speed of light in vacuum is given by the laws of electricity and magnetism. But for us, we'll just kind of cheat it. So example, for us, 1.33 would be equal to 300 times 10 to the 8th meters per second divided by the speed of light in water. So that would be how I would find that. So what that means, actually, if you kind of look at this really quickly, is light moves at less than half the speed of light in vacuum when it's in diamond. So light is actually just absolutely sluggish in a diamond. Unbelievable. So it turns out that's what that really means. So for instance, I'll just point out a wacky idea that turns out doesn't really work, but it's an interesting thought. So it turns out that white dwarfs are about the size of Earth. So this is the remnant of a collapsed star that's about, similar to what our sun will do. So our sun will turn into a white dwarf. And they turn into something with a radius of about 6,300 kilometers. And they're actually made out of, for the most part, compressed carbon. And compressed carbon is a diamond. So the idea, and nobody's ever been to a white dwarf and dug into it to see, but the theory is that the composition is diamond. And one way of figuring out whether or not that might be true, it would be really difficult to do, but this is the sort of wacky stuff that astronomers dream up, is you have really far off gamma rays or X-rays from some other exploding star or source. And the gamma rays, so they are light, that actually pass around a white dwarf will go through vacuum, so they'll go this fast. And the rays of light that go through the white dwarf will actually go more slowly, in fact, by a factor of over 2. And you can plug in the numbers, and what you would see is that these things would be delayed by 0.04 seconds. So if you've got a gamma ray detector that can at least resolve stuff on the 0.04 second level, you might be able to verify this claim as to whether or not these things are actually made out of diamonds. I wouldn't recommend trying to do it, but it's at least possible. So what we'll do next is do a couple of Snell's law problems. We'll do that in lecture as well. And then you guys have a whole lab on this. And spend a lot of time with total internal reflection. So total internal reflection is when we basically break refraction and the light beam comes in and then bounces off instead of makes it out of the second medium.